Thank you so much for coming. This is our today for MITAC 2024. Our first speaker this day is Mindy Yaneli Huerta Perez. The title of her talk is Question Categories with Exact Structures from N+2 Rigid Subcategories in Strangulated Categories. Thank you.
Okay, first of all, I would like to thank the organizer for this opportunity. Thank you so much. Secondly, thank you so much all of you for being here today and for your time. Okay, so let me start with this work. Okay, this work is a joint work with Octavio Mendoza, Corina Sáenz, and Valiente Santiago. And in this work, we study some quotients in X-triangulated categories. Okay, okay, so let me say first the reason that we choose this context. Okay, X-triangulated categories is a generalization of many contexts. For example, abelian categories, triangulated categories, exact categories, yeah. And well, wait a minute.
Permíteme. Ahí, creo que ya lo puedes mover.
Yeah. Okay, so a reason to choose X-triangulated categories is sometimes when we try to work in a subcategory, and you take the subcategory, the subcategory escapes from the original context. Yeah. For example, you have an abelian category, and you take extension clause subcategory. That subcategory, we can assert that subcategory admits an abelian structure. Yeah. But something that we can say is that subcategory admits an exact structure. Okay. Well, something similar happens, for example, in case of triangulated categories. Yeah. Yesterday, Dr. Gomez talked about triangulated categories. And in triangulated categories, you have a subcategory, which is extension closed. We can assert that the subcategory is again triangulated. Yeah? But something that we can say is the subcategory is X-triangulated category. Yeah. The notion of X-triangulated categories was introduced by Hiroyuki Nakaoka and Jean Palou in 2019. Yeah. And they took all the homological behavior that we can find, for example, in abelian, exact, and triangulated categories, and they gave a list of actions, yeah, which replicate the homological behavior in all that context. Okay, so this is a reason to work with X-triangulated categories, because you have, in some sense, when you take subcategories, you get again the same structure. Okay. Other interesting phenomena happens with quotients. Yeah, if you take a quotient in an X-triangulated category, it's very hard to say that the quotient admits X-triangulated structure. But some result for this kind of categories. We have, for example, this proposition by Hiroyuki Nakaoka and Jean Palou, and they say, if you have subcategory inside of this intersection, the class of projective injective objects, and you take the quotient admits an X-triangulated category, X-triangulated structure. Okay, but in general, if you want to study some kind of quotient, in general, we know anything about. Okay. Okay, so let me present the definition of the X-triangulated category. Yeah. When we talk about X-triangulated category, we need to consider three main ingredients. The first is an additive category C. The second is a bifunctor E from this cross category to abelian groups. Yep. And the third is something that they call a realization of E. Okay. For example, when we work with abelian categories, we can think in the category of left, right R models over a ring R. Yeah, we can define the first extension group. Yep. Yeah, like a bifunctor. Yeah, this is for abelian categories. And in this, we can consider a special kind of sequences, yeah, short exact sequences. Okay, what happened, for example, in triangulated categories? In triangulated categories, we can define a kind of first extension group in the category by using the home functor and the shift functor, yeah. And we have some similar to short exact sequences, yeah, called distinguished triangles. Okay, so here we have A, B, C, A, shift 1. Okay, what happened in triangulated category? We have the analogous of the previous two concepts, yeah. In triangulated categories, we have this bifunctor E from this cross category, double N groups. And this part plays the role of the first extension group in both contexts, okay? And we can replace distinguished triangles or short exact sequences for something called E triangles, yeah? E triangles, we will denote it by this point, okay? A, B, C, dashed arrow, okay? Well, so here we have the main ingredients and the main elements in this definition. And we also have the list of actions, yeah? Something that we can say is the action which appears here is very, very similar when we work with triangulated categories, yeah? For example, ET3 says you have two E triangles and you have that commutative square. You can complete that this diagram with a morphism from C to C prime such that the two inner triangles, the two inner squares commute, okay? And this is an action which appears in triangulated categories. Something special in triangulated categories is you need to consider the dual statement, yeah? Depending on the context that you take, sometimes you only need one of them, and you can prove the dual statement. But for triangulated categories, you need both, okay? For example, we have the dual of the previous action. For example, here, it's similar to something that you heard yesterday, yeah? For example, we have the analog of the octahedral action for triangulated category, but in this case, it's called ET4, okay? And we also need the dual statement, yeah. And for example, in a Boolean category, the octahedral action, in the case of triangulated or ET4, can be taught, for example, push out diagram, yeah, in a Boolean categories, yeah. The following is the equivalent of the pullback diagram in a Boolean categories, okay? And well, so as you can see, we have many, many things in common with other kind of contexts, yeah? Okay, so previously I mentioned something about the quotient, yeah? We have that in this special case, we can talk about the quotient, and the quotient is an exact category. But there are other kind of subcategories called too rigid and too closer to the subcategories, okay? What happened with this kind of subcategories? Well, first, we have here the definition, yeah? Consider an triangulated category and a subcategory X. We say the X is too rigid in case that this abelian group vanishes. And for any pair of objects in X, yeah. And too close to the subcategory is something that satisfies this condition, yeah. This condition has to do with left and right approximations, yeah. And you also have that this equality holds, yeah. This equality is determined by the vanishing of the first extension group, yeah. Recall that the first extension group in this context is the analog of the other first extension groups in other contexts, okay? So what happened with this kind of subcategories? For example, for this kind of subcategories, we have these two results. When you take a triangulated category and you take a two closed Dalton subcategory, you can talk about this quotient. The quotient is a volume, okay? On the other hand, we also have a generalization, but in this case, for the case of triangulated categories, yeah? If you have the triangulated category and you have a two rigid and precoding class, this quotient is a volume, yeah? So let me be more specific with this quotient, yeah? Then let me explain more about the opt and right, and up and down category, yeah? X check 1 is a subcategory, and we say that M belongs to this class if and only if, by definition, there exists a triangle with this form. Here we have the object, we have X0, X1, and that is a triangle, yeah? And X0 and X1 belongs to X, okay? Well, that subclass can be generalized for higher indexes. For example, if you want to describe M, X check N plus 1, M belongs to this class if and only if there exists a triangle with this form, M X0 M prime dash arrow, such that X0 belongs to X and M prime belongs to X check M. Yep. So we can define this class. Okay, so here we have the definition of this opt categories, opt class, and X between brackets means it's a class of morphism in your category. Yeah, you say that F belongs to this class if and only if there exists, well, F factors throw an element in X. Yeah, we have F, we have a commutative diagram with this form, and within X belongs to X. Okay, well, so that quotient is a volume. Okay, so okay, I mentioned some results for two rigid and two closed Dalton subcategories, but we also have the generalization of this kind of subcategories. Yeah, that is called M plus 2 rigid and M plus 2 closed Dalton subcategories. Yeah, but in this definition is worth mentioning the following. When you work with triangulated categories, you only have the first or the analog of the first extension group. But you can say that there exists higher extension groups, okay? So under some extra assumption, we can assert that there exists this kind of higher E extension groups. And in that context, this definition makes sense, okay? So here we have a very similar definition for M plus 2 rigid and M plus 2 closed Dalton subcategories, yeah? And so, on the other hand, I mentioned some results for two rigid and two closed Dalton subcategories. On the other hand, we have this kind of generalization. And from that, a question arises, yeah? For example, if it's possible to say something about that quotient when you take M plus 2 closed Dalton subcategories, yeah? In the case M equals 0, but, well, we have these two results, okay? So the question is, what happens if you take M more than 1, okay? For M plus 2 closed Dalton subcategories, and in a more general sense, if it's possible to say something when you take M plus 2 rigid subcategories, yeah? If you have M plus 2 closed Dalton subcategory, in particular is M plus 2 rigid, yeah? But the converse may not be true, okay? So in some sense, it's the same question, but with less hypotheses. Okay, so, well, for the rest of this talk, I will explain that under some extra assumption, we can say something about the quotient. But first, I need to recall the original proof of Soy-Su for the case M equals 0. Okay, so in Soy-Su proof, the authors take a triangulated category with enough projectives and enough injectives. They take a rigid subcategory X such that the class of projective elements is contained in X, yeah? After they take an element in this class, yeah? Here we have a definition of that class. And they take the defunctory, they fix the second variable by the element that you choose at the beginning. And after you take the restriction of X, yeah? that produce a contravariant functor from X to F to abelian groups. Okay, well, so after they took the stable category of X, yeah, here is the quotient category that you have, but in this case, you take X as the class of projective elements. Yeah, it's a particular case when you take X equals the class of projective elements. Yeah, so from this quotient, you have this quotient functor from X to the stable category of X. This is a stable category of X, pi, and pi has a nice universal property. Yeah. For example, if you take EPM, P is a projective element in your category. That is, well, this abelian group vanishes. Yeah. So by using the universal property of pi, you can construct a contravariant functor from this stable category to abelian groups. Yeah. At resume, for every element here, we can construct a contravariant functor from this stable category to abelian groups. Okay. Later, they use the previous construction and construct another functor, in this case from this category, to the category of right models. Right models here means are contravariant functors from this stable category to abelian groups. Okay. Well, so by using the previous construction, they can define a functor H. Yeah, here we have the correspondence. They prove that that functor is a well-defined additive functor. Yeah, and after, well, here we have H. Yeah, after they take this quotient category. Yeah, along with the projection functor. Yeah, and again by using the universal property that Px has, they can construct F, a functor from this quotient category to the category of right models of the stable category of X. Okay, so, well, after they study some properties about F, yeah? For example, they ask when you have that F is equivalent. So for that, they need to know what is the essential image of that functor F, yeah? And the essential image of that functor F coincide with the class of the finitely presented right models in this stable category, yeah? And well, after the last part is by using the functorial finiteness in X, they prove that this part is an abelian category. So we have an equivalence of categories. The right side is an abelian category. So through the equivalence, they can induce an abelian structure in the quotient. Okay, this is the general idea of Soy-Su proof. Well, so the first step that we tried was to extend this proof for the general case. Okay, so we can extend some part of that proof up to some little changes, okay? For example, we take a small triangular category. The reason of taking small is because we need higher extension groups. And when your category is small, you can assert that, okay? So I will take a small triangular category. I will take an n plus 2 radius subcategory, yeah. And we chain this part, yeah, this containment by the following class of morphisms, yeah. We consider this class. Notice that this class is determined by this condition, yeah. That condition is very, very similar when you think about projective elements, yeah. But in this case, you are taking morphisms, okay? So we, in some sense, chain projective elements by projective morphisms, okay? Well, by using that, we follow the same construction, yeah? In this case, we take this class and check n plus 1, yeah? Recall when in the case n equals 0, in this case, we have an x check 1, yeah? So in some sense, this class can be bigger, yeah? After we have the same, we take the same construction, we take this functor, contravariant functor. We notice that when you put here E, F, M, and F is a projective morphism, that well, this functor vanishes. So we get a contravariant functor from this stable category to abelian groups, okay? And well, so After, the same. We have the functor H, yeah. Here we have the functor H. And this is, here appears the first difference, yeah. In the previous construction, the authors take a quotient, but the quotient is very, very explicit in the down category, yeah. The down category corresponds to this class. But in this case, I take a K, and K is the kernel of H, okay? The reason to take that is because I need to use the universal property of pi K, okay? So by using that, we get a functor F from this quotient category to the category of right models over this stable category, okay? And well, the following step was to study some properties about F, yeah? For example, we notice that K corresponds to this class, yeah? The class of morphism with factor through elements in X, yeah? And that is the same description that we have in the case of Soisu proof, okay? So that part doesn't depend on the index that you take, okay? Well, the hard part was the following. For example, describe the essential image of F, yeah? The essential image of F corresponds to functor G such that admit exact sequence with this form, yeah? These two functors are home functors, yeah? And you fix the second variable, yeah? X0 belongs to X, X1 belongs to X check N, yeah? And when you take N equals 0, that coincides with the description of the finitely presented right models, yeah? So again, all these are coinciding with Soisu proof, yeah? With this part. Okay. And well, the last part is under what assumption we can assert that we have the equivalence, okay? And the answer is the following. You just assume that X is closed by taking finite coproducts, and you also assume that X check N has enough a projective morphism from X. That can be taught, for example, in your category when you have enough projectives, yeah, but in this case, you chain projective elements by projective morphism from an element in X, okay? Well, under this couple of assumptions, we can assert that that is an equivalence of categories, okay? Well, so in this sense, we have an equivalence of categories, but we know until now that if one of them admits some kind of a structure, okay? For example, this is the hard part, and the part that we can appreciate something that the case N equals 0 hides, okay? For example, in general, we have this chain of containments, yeah? In the case N equals 0, the first inclusion is an equivalence, is equality, sorry, yeah? And by using the functorial finiteness, this part is an abelian category. But what happened for higher indexes? For higher indexes, this inclusion may be strict, and we know that this part is an abelian category. So, well, okay, so something that we can say is, for example, if you see R and X inside of this category, the category of right models over this stable category, this category is an extension closed category, yeah? And this part is an abelian category, yeah? So, but something that I mentioned at the beginning, you have an exact extension closed category in an abelian category. So we know that that admits an exact structure, yeah? So from this equivalence, we have the equivalence of category, we have the right side is an exact structure, is an exact category. So through this equivalence, we can induce an exact structure in the left side. So in general, for higher indexes, we can say that the quotient, the respective quotient, admits an exact structure, okay? well, so let me finish with an example. Imagine that you have this lambda is this self-injecting Nakajima algebra associated to this quiver with this relation. Yeah. So we can construct the category of the mod lambda, the category of finitely generated lambda models. Yeah. And we focus our attention on the stable category of mod lambda. Yeah. Well, that subcategory mod lambda, the stable category of mod lambda, it's known for being triangulated. Yeah. And I will take extension plus subcategory in this triangulated category. Yeah. Because I know that I take extension plus subcategory in a triangulated category, I have them an extrangulated category. Okay. So, well, by using a powerful tool of lambda right-hand theory, yeah, we can describe this category, yeah, in the following picture, yeah. In this picture, you can see all the decomposable objects in mod lambda stable, and every arrow here corresponds to a irreducible morphism between two indecomposable objects, yeah. So, okay, so take this picture, see this picture, and as you can see these two lines, this part and this part, yeah. See? Can you see? Well, so in this part, consider all the objects between these two lines, yeah? Club suit and sped suit, I don't know the name of that symbol, but consider all these part of elements, yeah? Along with this isolated point, start point, okay? Well, one can prove that is a extension close category in a triangulated category. So C is a extriangulated category by using the theory. Inside of C, consider X, these two lines, yeah? And one can prove that X is a 4-rigid subcategory, yeah? And all the requirements that we need to get the equivalence are satisfied. And moreover, we have that for every index, yeah? For example, you have 4 rigid, in particular, you have 2 rigid and 3 rigid. And this is an example that we can apply the previous equivalence 3 times, okay? So in this case, we have 3 quotients for every index from j from 0 to 2. Okay, what happened for the case j equals 0? The case j equals 0 coincides with Soisu result. We know that the first quotient category is abelian, but what happened, for example, for the case j equals 1, yeah? In this case, we can appreciate the difference with the previous result by Soisu, yeah? By using, again, this description by the Karkak, we have that this quotient is determined by all the relation between red points and all the arrows between them, yeah? We know from the previous equivalence that that quotient is an exact category, yeah? But something that we can say is that quotient is not abelian, yeah? And the reason is there is at least one morphism, the morphism is here, yeah? That doesn't admit a cokernel, yeah? So in general, for higher indexes, we can say that the quotient, the respective quotient is an exact category. And we can say that strictly speaking, yeah, because we have some examples that where do have exact structure, but it's not abelian in general. Okay, and well, so here we have a list of reference, and thank you so much for your time.
Thank you so much, Mindy. Questions, comments? I would like you to a question, a silly question. In your definition for rigid, I think is that
Rigid?
it's at the beginning. At the beginning.
Only
Yeah, cluster thinking.
see.
For me, it's curious. Do you know what is important? The second point.
The second point,
Yeah.
this condition?
I think it's the following. Where do you have the intersection of all verbs?
Uh-huh.
I think it's the following
The
definition.
importance of these two conditions, or in general? Well, when you talk about recording and pre-enveloping class, in some sense, you can approach every object. Yeah, for every object, there exists some special kind of morphism, which has a factorization property, and that is very, very useful to construct some proofs.
Okay, thank you. Because I'm thinking about in general,
Mhm.
in the case of abelian categories and X conditions, X projective,
Mhm.
X injective, and for me, it's like you are asking for to have the two conditions at the same time, like that. It's
Well,
like that?
under some extra assumption, you can translate factorization properties to the first extension group. Yeah, maybe it's the relation.
Oh, thank you so much.
Okay.
So we have 5 minutes and then our course. 5 minutes. Well, thank you. Our next speaker is Sebastian David Melzer, and the second day of his workshop, Priestley dualities and its applications to point-free topology.
Thank you for the introduction. So I just want to start by quickly recapping what we talked about last time. Okay. So we went over the background. We talked a bit about point-free topology, stone duality, and spectral spaces, and then we started talking about Priestley spaces, and we ended more or less right before we started talking about Sakya. And in particular, we talked about how the functor points can assign to each frame a space, but that space is not always really a good representative of that frame, because a frame might not have any points or not enough points. So one alternative that I mentioned is you can look at the category of locales, consider that your representation of a frame as kind of space-like object, but locales don't really have a point-based intuition like topological spaces. So for that purpose, I introduced stone duality for bound distributive lattices, because that can be restricted to the category of frames, and you get some kind of spectral spaces that represent frames, and you have a faithful or good representative for each frame. But that was not the point. That is not the framework I want to work in. I want to work with the category of Priestley spaces. So that's what we ended up. That's where we ended talking last time. I want to continue talking about Priestley space and really focus on the properties that Priestley spaces of frames possess. Okay. So if you remember, I gave this last time as homework. I don't know if everyone did their homework. But this is a well-known fact. And the duality for Heyting algebra was developed by Leo Sacchia. I always admired Leo Sacchia for some reason. I have never met him, but he always seemed like a cool guy to me. So that's why I included the picture. It's even why I went to New Mexico to study under Gurm, because Leo Sacchia was Gurm's advisor. And even my master's advisor was Nick Bezhanishvili, so I had both my advisors were students of Leo Sacchia. Yeah, but that's just a side note. So Heyting algebras are special bound distributive lattices. So we can look at the Priestley spaces of Heyting algebras and see what characterizes them. So the special thing about Heyting algebras is that you have this implication. So if you have a Heyting algebra and it will be isomorphic to the Clopen upsets of its Priestley space, this implication will exist in the Clopen upsets. But how do we calculate this implication there? So we can, if you did your homework, you know that implication can be defined like this if you have a frame, at least. But this is something that is always true in a Heyting algebra. This implication is the join of all the elements C. If you meet them with U, then it should be below V. And this implication will be the biggest element that does that. You can rewrite this to this form. So take the biggest C that is below V union U complement. So this is even how we define implication in a Boolean algebra. So U implies V would be not U join V. But that does not work in a Priestley space, because the complement of a Clopen upset is not a Clopen upset. So this union is not going to be a Clopen upset. But this thing, if it exists, is going to be the largest Clopen upset contained in whatever this set is. So if you there's this kind of expression we can use to calculate the biggest upset contained in a set Z. It's you take the complement, then the downs, and then the complement again. So if I plug in for Z this V union U complement, what I get is some very ugly expression. But if you look carefully, you have like two complements here, so you can distribute this complement inside and turn it into intersection. And if you have, then you have U intersection V complement, that's the same as U Z minus V. So this thing should be somehow downset U Z minus V complement. So if I intersect two clopens, that's going to be clopen. But if I take the downset of a clopen, it might no longer be clopen in a Priestley space. So the only thing here that breaks clopenness is this downset. And what we get out is going to be an upset. And so I take a downset, so it's always going to be a downset, take a comment, it's going to be an upset. So I just need to preserve the clopenness of this thing. And that's exactly what we need for it to be in the Sakya space. That's the downset of a clopen must also be clopen. And then we can calculate this nicely. This thing is just that. So that's what brings us to how a Sakya spaces are defined. The Sakya space is a Priestley space such that whenever you have a clopen U, the downset of that thing is also clopen. That makes sure that the implication exists. And there's an equivalent characterization that will be, it's nice to point this out because there's connections with how we'll define the Priestley space of frames. So if you have a Priestley space, then it's in the Sakya space if and only if the closure of every upset is, again, an upset. Closure might not necessarily make some keep upsets, but if you're in a Sakya space, that will happen. So a Sakya duality is for Heyting algebra and Heyting homomorphism, and a Sakya space and a Sakya morphism. I'm not going to discuss a Sakya morphisms because frame homomorphisms do not preserve Heyting implication necessarily. So I want to look at slightly different categories in this framework. I will change this category to the full subcategory of distributive lattices. So I just take bounded lattice homomorphisms. And for a Sakya space, I will just take Priestley morphisms. And it's pretty straightforward to show that these will also be dually equivalent. You just restrict the equivalence between the Priestley duality. So then I can make this picture. Or I could have made this picture with the other categories too, but I want to put frames below here. And if I take the added categories, that's not going to work. So I have Priestley duality and I have a Sakya duality with different morphisms. And the next goal is to put frame in the next row. So we know frames are complete Heyting algebras. So this Priestley spaces will be a Sakya spaces, but they will also have this, what corresponds to completeness. So we want to understand what arbitrary joins mean in a Priestley space. So the fact is that if you have a distributive lattice D and Priestley space X, and the join S exists in D, it means that this thing is open. So that is the image of the set, the union, the closure, and then the upset. So remember that phi maps elements of D to clopen upsets of the Priestley space. So this is a collection of clopen upsets. You take the union, that will be an open upset, and the closure, and then the upset, that should be a clopen upset. So we also talked about the spectral spaces. So if I have a Priestley space, I can look at the spectral space X and the topology given by open upsets, where the compact opens were exactly the clopen upsets. And since spectral spaces are coherent, that means the clopen upsets form a basis of the spectral space. So every open upset is a union of clopen upsets. And that means that instead of having this condition to characterize completeness, I can write it a bit simpler. I can say D is complete if and only if upset closure of U is clopen for each open upset. So I don't need this more nasty looking thing here. I can just talk about arbitrary open upsets because they're all of the form union of open upsets. So this characterizes completeness for Priestley spaces. In this situation for hiding algebra, it's a bit easier because remember the closure of an open upset, there is already an upset. So we don't need the upset on the left-hand side anymore. So our corollary is that if you have a hiding algebra, it's going to be complete if this thing is closing for each open upset. And we don't need this extra upset here anymore. So that simplifies the definition or the condition. I also want to point out that every Boolean algebra is a hiding algebra. So we can restrict this also to Boolean algebras. What happens in Boolean algebra is that the order of the Priestley space is just discrete. Every point is, there's no order basically. So then open upsets are just open sets. So a Boolean algebra is complete if and only if U is closing for each open set. And this is known as the spaces that I have this probably are called extremely disconnected. This is a well-known thing. And so we know that complete Boolean algebras, their stone space correspond to extremely disconnected stone spaces. So since our condition is kind of similar to this, it is called extremely order disconnected. It's just the order analog of being extremely disconnected. So this gives us completeness. So now we really know what the Priestley spaces of complete hiding algebras are. They are Esakir spaces that are extremely order disconnected. So now I can start talking about Priestley reality for frames. We have collected all the ingredients, so we can cook up the definition or the characteristics. And what you can show is that if you have a distributive lattices, a bounded distributive lattice, its Priestley space is an extremely order disconnected Esakir. I mean, I said it right, but I didn't read the proposition correctly. I want to say that if you have a lattice, this is going to be a frame if and only if the Priestley space is an extremely order disconnected Esakir space. The proof right now is very simple because we have those two lemmas from before. We know these are frame if and only if it's a complete hiding algebra. We know its Priestley space is an Esakir space because it's hiding. It's complete if and only it's extremely order disconnected. So this is a very straightforward proof right now. And so we could define our Priestley space of frames to be exactly extremely order disconnected Esakir spaces. I want to make the definition slightly simpler than that. So I will use this lemma. A Priestley space X is an extremely order disconnected Esakir space if and only if the closure of U is a clopen upset for each open upset U. So if you compare that to the definition I had, or the equivalent definition for Esakir spaces, it said that this is a upset for each for each upset. And what I'm adding here is I'm adding open and I'm adding clopen upset here. So it strengthens that equivalent condition for Esakir spaces. And that's how I define L spaces. An L space is a Priestley space that satisfies this condition. So L spaces are what I call, or the Priestley spaces of frames I call L spaces. The L stands for locale, localic space. So I guess I forgot I had this on my slide here because I already mentioned it, but you can compare this definition to this one. I think it's even possible to add open here. I'm not quite sure, I didn't check. And then they become even more similar. Huh? Here. You can add open upset here. Oh, yeah, that's what I thought. So this is also equivalent to just saying it's an upset for each open upset. So in fact, you're only adding the fact that this should be a clopen upset for L spaces. So remember the goal was to get this topological representation for frames. And we have kind of achieved that. We have found these Priestley spaces. And we have not talked about frame homomorphisms because Priestley spaces just have Priestley morphisms which correspond to bounded distributive lattice homomorphisms. So they're not necessarily preserve arbitrary joins. Don't want to go into the details of this, but if you have a Priestley morphism, you can show that the dual map is a frame homomorphism if and only if it commutes with closure, the inverse, for all open upsets. So it doesn't need to do it for all sets, just for open upsets. It's because open upsets kind of represent these pre-join things, and once you take the closure to join, because inverse image will always preserve union, and you want to pull out the whole join, you need to pull out the union and the closure. So that's where this comes from. It's quite just natural translation of what it means to preserve joins. And we just define L morphisms to be the morphisms that do this. I wrote closure in a different way here, but this is also just supposed to be overline. So my category will be L pre's, look, L spaces and L morphisms. This was first shown by Pulte-Sichel in 1988 that these two are equivalent. And they have a bit different setup because they basically have everything upside down. But you might say I have everything upside down. But for them, everything is kind of clopen upsets. For them are clopen downs because they have everything defined dually. So the proof of this is simply you have these functors that establish pre-duality. By the lemmas we have, they restrict on an object level to frames and LPs, and even on a morphism level, that they're well defined. And the units, they simply become frame homomorphisms and L morphisms in these categories. So that means that this equivalence will be strict. So we arrive at this diagram now. We have Priestley duality, we have Esaki duality, and we have Pulte-Sichel duality. It is just bounded lattice homomorphisms and Priestley morphisms. So these are full subcategories of these two. And here, these are not full subcategories because you have different morphisms. But I don't want to use the usual morphism because then I couldn't restrict here. So now we have objects, we have the morphisms, so we have the real category that represents frames. That was the goal of this course, introduce a framework in which every frame can be faithfully represented as topological space and reconnect frames with their point-based intuition. So from now on, I want to show some examples of how we describe point-free notions in this framework. So if you remember, in the beginning, I had this example of a pointless frame, this complete atomic Boolean algebra. I added countable to this to make it a bit nicer for myself, because they are all the same. So then I have a unique Priestley space that corresponds to it. Again, because they don't have atoms, they don't have points. But the Priestley space of this is actually the Cantor space with discrete order. And that is something that has been studied a lot, the Cantor space. So this Cantor space gives us a lot of information about, it gives us a point-based intuition about what this frame is. I'm not going to prove this because I'm maybe too lazy, but it is true. Discrete just means this order is just equality. So if X is different from Y, there's just no order between them. So it's because this is a Boolean algebra, so the Priestley space is just going to be a stone space. It doesn't have really any order. So First, I want to start talking now about spatiality. How do we talk about spatiality in this setting? We have a frame L in its Priestley space. We can embed the points into X, the points of that frame. I say without loss of generalities, embedding is identity. But if you remember, I defined the points of L to be the collection of completely prime filters and X the collection of prime filters. So points of L actually sits inside X as a subset. So this embedding is identity. I don't need to assume anything on it. If you had some kind of different definitions for these, you might need to do some embedding. In my case, I don't have to do that. It's just identity. So this set lives inside X. But I really also want to understand where the topology comes from on this thing, because it's not, obviously, or I don't want to spoil the future. So I want to know what the topology is. Is it the subspace topology of this? That's an option, but it will not be. And before that, I want to really understand, how do I pick out these completely prime filters? How do I pick out the points of the frame in the language of the Priestley space, in a topological language? So the thing that happens is that a completely prime filter in my space, or a prime filter in my space, is going to be completely prime if the downside of it is cloping. And usually in a Priestley space, you have this fact that the downside of every closed set is closed. Singletons are closed, so the downside is closed, but they're not necessarily open. So this adds that the downside of a point is open, and those are exactly the points of my frame. I wanted to prove this, but then I was in a bad mood, so I didn't prove it. But if you want to see the proof, I like the proof, but it's a bit, there's some steps. So we call these points that satisfy this condition localic points. Because for me, I don't really want to talk about frames all the time. I don't want to call them completely prime filters. I just want to think of points of my space and special points of my space. So we now really know what these points of my frame are, but I also want to know what is speciality. If you remember, speciality means having enough points. So if I ask you, what does it mean in a topological sense to have enough points? What does it mean for a subset to have enough points? So you might think of rationals and real numbers. There are enough rationals to fill the space of real numbers with density, right? Right, that's what this means too. L is spatial if this set of localic points is dense. So I always find this fascinating that this is how it works. So this is exactly what it means to have enough points in a topological sense. And it really corresponds to being spatial. Because yes. I can't yet tell you the story why it is called localic point. It's because my referee didn't like the previous name. It was just point. And he said he's confused because a space has points. So if I just call these points, then how would I call the things just in the Priestley space? So he recommended I add an adjective, and he recommended localic because these are the points in the locale. They are also called nuclear points. We can see that in the future when I start talking about sublocales. But yeah, at this point, there are called localic points in my work. And for the same reason, we call this collection of localic points the localic part. And this was previously called the spatial part. But the referee thought that every space is spatial, so you can't just call a part spatial of a space. Because X itself is also a space, so this should not be called the spatial part of a space.
The proposition there L is any local and but X,
X-
what's the relation between X and L?
X should be the Priestley space of L. Yeah, I guess I could have written it. Whenever it's not mentioned, that's what's gonna be the relation. So whenever I have a proposition with L and X, the L is gonna be L is the frame, X is the Priestley space. And I also have this new notation of if I mention Y, it's always the localic part of X. So it's always the points of the space of points of the frame in a way. So we know this set, but I want to know what the topology is. Where do I get the topology of the space of points from my Priestley space? And because it's not the subspace topology inherited from the Priestley space, in fact, what happens is the subspace topology inherited from the spectral topology on X. So that means it's the restriction of this topology, the open upset topology. And if you think about the topology of the space of points, it's this: you have an element in the frame, and you take all the points that contain that element, right? The elements in the frame are your open sets. But the elements in my frame, in my Priestley space, are the clopen upsets, right? So the topology should come from the clopen upsets. And unions of clopen upsets are open upsets. But the fact is, so I don't want to work with the subspace topology of the spectral topology. I think of this topology in a different way because of this lemma. If I have an open upset of X and I intersect it with the localic part, the closure of that open upset with the localic part is the same. The closure of an open upset does not pick up any localic points. So in fact, the topology can be defined like this. I take all the cloven upsets and intersect them with the localic part. So these are exactly the elements of my frame in a way. The cloven upsets are isomorphic to the frame that I started with. So this is essentially that Stowe map that we have for frames. What I always find it fruitful to point out that it comes also from the spectral topology. It's just that once you're in the localic part, you no longer see the difference between cloven upsets and open upsets.
So the points of the frame, not a subspace.
Yeah, it's not a subspace now. It's a subspace. If you look at the Priestley space as a spectral space, then it is a subspace.
That map you had was not really embedded. Just an inclusion of sets.
It's an embedding in the category of sets. So it's, yeah, I guess I should have made that clear. It's not an embedding of oh, where did I go? Did I say where did I say this? Well, I guess this was very misleading. I apologize. But yeah, it's just an embedding of sets. So, and this is one of the reasons why it might be nice to work with spectral space, because there it is actually a topological embedding. The problem is the category of spectral space does not have continuous maps as the morphisms.
So you can't promote that ever to an embedding? Like topological speaking?
If you think of X as a Priestley space, or this will not become a continuous map. There might be strange situation where it happens, but it's not. If it's a Boolean algebra, I guess it will become a continuous map, because then the spectral space and the Priestley space are the same. So, and then it will happen, I guess. So I guess I can ask because by saying if L is a Boolean algebra, then this becomes an embedding in the topological sense. But not before that. Let's go back where we were. So I want to talk about simplification, because it's also related to this picture where we talk about the localic part. So remember that if you have a topological space, you can look at the points of the opens, and we call it the subification of X. How this is viewed in the picture of the Priestley space, if you have Z to be a topological space, then you can map Z into the Priestley space of the opens with this map that maps a point to the completely prime field of opens that contain that point. So again, this is not going to be continuous, but it's some set embedding. But if you look at this set inside the Priestley space, it's going to be a subset of the localic part because it consists of completely prime filters. And it's going to be equal to the localic part if and only if Z is sober. So the subification is really looking at the localic part of this Priestley space of the opens of your space Z. I was thinking about this recently because of some problem I'm working on. I don't really have details about that problem, but so I wanted to give this example, but I didn't have time to draw the picture. I guess I could do it on the board, but if you have the cofinite topology on natural numbers, what the Priestley space looks like, it will be all the natural numbers or the completely prime filters generated by a natural number, and then you have this extra point on top, and every point sees that extra point. And this is also going to be a completely prime. It's the completely prime fit of all the cofinite sets. But this point is the subification point. This point is going to be in the localic part. So in this is my Z, and this whole space is my Priestley space. What happens always is if you have a subification point, it will always be pushed above the space you started with. This is not really part of my story, that's just part of my problem. But what I wanted to point out is that this set Z is dense in my Priestley space, but that does not mean that this is a sober space. One of the bad thoughts I had in the beginning when I started working this was thinking, if my space is dense, it's going to be sober. Because the localic part being sober means it's a spatial. But of course, if I come from any space, my localic part should be dense. Yeah, but let's not worry about that, I suppose. Let me go back to my story. So we talk about speciality now. I want to talk about sublocales. I think a lot of people are interested in sublocales. And I want to show you how they look like in a Priestley space. Just a quick reminder what sublocales are. They're a subset of a frame that is closed in the meets, and this hiding implication somehow goes inside it, but for all elements of L. I find this condition always very hard to remember. And the condition for nucleus or for the Priestley analog is going to be, it's easier for me to understand. But sublocales, they're the point field analog of subspaces. But we have this other characterization of sublocales in terms of nuclei. So there are maps on a frame that satisfies the three conditions. This is not really important for my presentation. But usually what we do is we translate nuclei into the language of the Priestley space instead of sublocales. But because nuclei and sublocales are the same thing, it's also the characterization of sublocales. So how do we characterize these nuclei in a Priestley space? We look at special closed sets, and we call them nuclei because of nucleus. And what I do is, if you have any clobin of my Priestley space, I intersect it with the set and take the downs, it should be global. So they should kind of behave like an Asakia space for the bigger set. So whenever I pick any global intersect with the set, the downside should be global. And this is a theorem, didn't put any authors. The problem with this theorem is that it was proved in a different language. It was proved by, I think, Grom and Silvio Gilardi, but they were looking at it from a different perspective. They were talking about what is called a subframe, but not subframes how we think of it in point field topology, but subframes of a Kripke frame. But that's where this theorem comes from. What I really want to point out, how do you go from a nucleus to a nucleus subset? If you have a nucleus, the nucleus subset is the set of these points. So the points that whenever JA is in the prime filter, A is also in the prime filter. So they kind of respect this chain the way that whatever is seen by J, it should see the pre-image. See how much time I have. So this slide, so I want to make some disclaimers that I did not check everything on this slide that follows now. This was something I thought of last night, and I couldn't really find the right references to verify it. I couldn't, but I think it is correct. But if it is not, don't cite it in any of your work, I guess. So there's special nuclear subsets, like every Klopen set is a nuclear subset. So Klopen upsets are nuclear upset. Klopen upsets are nuclear subsets. And what it corresponds to in sublocales is open sublocales. Klopen downsets correspond to closed sublocales. Klopen sets correspond to a meet of an open and a closed sublocale. Okay, these three are pretty well known, I suppose. For a while, I was thinking about what are complemented sublocales in my Priestley space. My guess was always that they're just the Klopen sets because the complement of a Klopen is Klopen, so then the complement is also a nuclear subset. But because the meet of two nuclear subsets is not the intersection, that is not really what happens. And if I understand it correctly now, the complemented sublocales are the regular closed subset of my Priestley space. I find that very interesting because I was wondering about what are these complemented sublocales. Yeah, but this is, I'm not sure about this. So let me just say that. But that's my conjecture right now. So this is why they're also called nucleic points. So if you have a localic point, you can show that they are nuclear subsets. They're essentially the smallest possible nuclear subsets. So they will correspond to joint irreducible sublocales. I'm running out of slides. I have one more thing to say. I wanted to end with some nice theorem that's also well known to you. So we call a sublocale dense if 0 is in it. And a nuclear, so this is a lemma, a nuclear subset corresponds to a dense sublocale if the maximum of the space is inside of it. So we call it cofinal. If it contains the maximum of the space, it's called a cofinal nuclear subset. So what you can show now is that max X is the least cofinal nuclear subset because there will be no smaller set that contains max X. That's literally, but this is literally the smallest set that can be cofinal. Turns out it's also a nuclear subset. So if you think where this will go, it will go to Isfell's density theorem. Because what happens is max X is the nuclear subset corresponding to the sublocale Booleanization. I was also planning to prove that, and then I didn't have the energy anymore. So I guess I failed my proof quotum today. Oh, I got with something. Well, yeah, this is what you have to do. But I find it a quite elegant proof of this theorem, even though I've been told it's also easy to prove in point field topology. I've never done it there, so I don't really know. But that's where I end today. Okay.
Thank you so much, Sebastian. Comments, questions?
So thank you for the talk. You mentioned that localic points are the joint irreducible of these sublocales. Do you know something about the mid irreducibles? Are you expecting that that is not going down, so they're up, or something like that?
I don't want to say anything because I'm not sure.
Okay.
It
Okay.
might be some kind of no, I don't. I'm sorry, I
Okay.
don't want to
And
say anything wrong.
and the second question is, I didn't really follow the when you were drawing the natural numbers. I think that it was the cofinality of the natural numbers, and then you put it points which are dense, and you put it one up. What does it mean? It's just that what
Um,
were you drawing there?
Yeah, that was
It's just that probably
so you have the natural numbers, right?
yes,
With some topology.
yes.
I just drew the Priestley space. So for each natural number, you have this point, right?
Yes.
So these are this point. So I call this one, I identify this one with the natural numbers. And the order is just subset. So
Yes.
lambda n is not going to be contained in any other lambda m. So all these numbers, they just sit at the bottom. And so on. But you also have another prime filter. The collection of all the cofine subsets also forms a completely prime filter.
Okay.
And that is the point here. So that is, I guess, all the cofinite sets.
Okay.
And but these are all contained in here because
Yes.
lambda
Yes.
n.
It's the cofine. Okay.
So that's where this comes from. That is the relation on the Priestley space. So I guess this is called an Hesse diagram.
That's right. Yes, yes, yes. So I was wondering because there was not a bottom thing, but it's just because you are looking only on the conformality
Yeah.
and not the order. Okay, thank you.
Can I go back to the speciality
Yeah.
problem? So it says that the frame was spatial if the set of points of the frame was dense in X, right?
Yes.
In its Priestley space. So that says that the opens of, well, like with the subspace topology, the points of L have the same opens as those of X, right? Because any open of X would have a point.
Yes, it's because opens of X. So remember that we're in the patch topology, right? So my basis looks like this. And all these contain enough points.
Right,
So-
right. But I guess what I was trying to understand if, like, to get a condition on L being spatial, is that its points as a subspace of the Priestley space has the same frame of opens as X.
As X.
Yeah, as the Priestley space.
Yes.
I mean, that's what that says, right?
Yeah,
Okay.
that is correct. I just never think of this localic part as a subspace of the Priestley space, but yeah, that is correct. But the frame of opens of the Priestley space is not really something we care about, because we care about this frame that comes from. We're looking at the Priestley space of a frame, so I really care about that frame of opens. But that's not the frame of opens of the Priestley space.
Yes, that's right. But yeah.
But the frame of opens of the Priestley space will be the same as the frame of opens of this Priestley subspace of localic points. Is that your question?
Yeah, I mean, we're just thinking that there's some, I don't know, there's some extra or nice topology, let's say, in points of L that just copies X, like as a topological space, the Priestley space. But it has nothing to do with the topology that has points of L, right? It has complete prime.
Yeah, it's not even. So I want to say something like, oh, it's the patch topology of this spectral subtopology on that thing, but that doesn't happen. Those things do not commute like that.
Okay.
So there's not. I haven't really looked much into that. All I know is it's not. One conjecture I had was a point that. So I have this Priestley space, right? And I have Y, and I have the spectral space. And the spectral space of, or not the patch construction on this space. It's called pi. So I guess my picture is wrong. This is the spectral space X. This is the Priestley space. This is the localic part. This is the patch construction of the localic part. What I thought is that this diagram kind of commutes, but it doesn't.
It doesn't.
No. So taking the subspace and then the patch is not as taking the patch and then the subspace. Yeah.
Thanks.
So thank you so much. We have a coffee break, 30 minutes. Tenemos un descanso para café de 30 minutos. Eh, Uh, hello, everyone. We're going to start our second workshop. It's Ranjita Ravi Prakash. Second day, the title is McKinsey-Tversky Algebra. So thank you so much, Ranjita. Can you go to G higher separation? Can you go to page? Oh. Oh, can you go to 3? Click on 3. Oh, it's okay, I can just. Yeah. Okay. Oh no. Then go. Okay, it's fine. Hello everyone, thank you so much for coming again. I'm gonna start by recalling what I did yesterday, but let me just. Sorry. This one will be there. Okay, this is where I will start, but I just want to recall whatever I did yesterday. So for me, T-naught algebra was if every element looks like join of meet of opens, meet closed. So U, V in opens. So if it's T-naught algebra, if every element is join of saturated, meet closed, and T1 algebra, sorry, T half algebra, if every element is join of open, meet closed. So that's T half. Instead of saturated, if I take open, it's just T half. And then T1 is just join of closed, just join of closed. And then T2 is the funny looking one. So every element is join of BI, where BI looks like feet of diamond box C. BI is less than or equal to box C. This is what I kind of did yesterday, but I did it in a topological space way. So this is T0, T half, T1, and T2. So today we are going to start off with higher separation axioms like T3, T3 and a half, T4. And you will see from T3 onwards, it sits very well with frames and topological spaces. It's almost very similar to what we have in frames and topological spaces. So, and today I'm going to be doing a lot of simple proofs so that just to get the gist of how to work in empty algebras, how to work with box and diamonds. It's pretty easy. So I just want to work a little bit of easy proofs today. So we'll start off by what is well inside relation. A frame L is regular if A is, all the elements of a frame is join of elements such that B is well inside A. What I mean by well inside is we say B is well inside A if B pseudo complement join A is 1.
that is star is pseudo complement. B star is join of all the elements such that, I should have changed it to B. C meet B is 0. My B star should have been join of all the elements such that C meet B is 0. This is called a pseudo complement of B. And then I am going to define a very similar relation, but it doesn't look like that. So I don't have a name for it, so I'll just call it triangle. A, B in an empty algebra, A triangle B provided diamond A is below box B. I'm going to be using this definition throughout to prove some of the things I have. So this is, I think, pretty easy to see, but I'll just walk you through. So A is triangle B, then diamond A is below box B. But box B is below B, right? And then A is below diamond A. A is smaller than diamond A. Box B is smaller than B. So immediately it follows A is less or equal to B. And then this is also very similarly it follows because 0 is always below all the elements. 1 is always above all the elements. And then it just pretty much follows. And then this is also pretty straightforward to check. It's not, it's just decoding this formula we have. This is also very straightforward to check, but I just want to show how to work with these empty algebras a little bit. Suppose A triangle B, if and only if, this is just the definition, diamond A is below box B. And then, if and only if, negation box B is below negation diamond A. I just negated the equation. And then this is nothing but box is negation, diamond, negation. Diamond is negation, box, negation. So this will immediately follow diamond negation B is less than or equal to box negation A. So this is nothing but negation B is triangle negation A. Just by doing normal calculations. And then this is also pretty straightforward. We can easily check this one. These are all the properties which this triangle satisfies. So what is regular algebra? Regular algebra, one, if it is a T1 algebra and all the opens are join of opens such that B triangle A. Why do we need to add this T1 condition is once it's opens are frames, it's the same as before, we will see that in a while how it is. But I need this T1 algebra because I want to generate everything with closed. But this V is nothing but open. The moment I have that open, I can immediately generate it. So if you actually think about it, the negation of the open will be meet. Negation of join is meet. So you will have join of meet. So everywhere I have join, meet of something, join, meet of something. So in order to do all of it, we have T1 there. But in topological spaces, if you see any topological book, they actually sometimes consider just T0 for regular. They don't need T as strong as T1, but they do take T1 plus regular to be T3. But here, I cannot do it for T0. T0 will be very weak. But however, I can restrict my T1 to be T half by showing that it's a subfit. Because T half plus subfit, we saw yesterday, I don't know if you remember, will give us T1. So T half is actually enough for us to define a regular empty algebra. We'll see how. Suppose A, B is in open, A is not such that A not below B, A is not below B. Then by this condition, I will get some element open C such that 3 is triangle A and C is not below B, just by this condition. and I pick my element D to be box negation of C. The moment I add box, it becomes open. So then D is open. So then D join of C will give me 1, and D join of B is not 1. Okay. So this will give me that M is a subfit. And yesterday we saw every subfit plus T-half algebra is a T1 algebra. So immediately we get T1 algebra. So T1 was not actually necessary. T-half would have done the job. And then to compare the regular algebra and regular frames, I'm going to prove that this triangle and the well inside relation, they both actually agree upon the opens. They both are the same. So I'm just going to prove that. A, B are opens, and A triangle B, if and only if diamond A is less than or equal to box B by the definition of the triangle, but my B is open. So this is just B, box B is just B. And then this is negation diamond A join B is 1. If and only if box of negation A join B is 1. Okay. And so the only thing I have used here is this part. So this one is diamond A is below B. So negation of diamond A join B will be 1. But again, negation of diamond is box negation A join B. But I'm saying box negation A is A star. Because if you remember what A star was, my definition, it's right here, right? This is my A star. So I want to write what actually box of negation A is. This is join of all the opens such that this is the definition of box. It's just like how we do in interior. If you see, oh. Okay. So it's just like interior. When we have an interior of a set, we take union of all the opens below it, right? That's exactly what I'm doing here. It's an interior operator. So it's join of all the opens below it. And this I can rewrite it as B meet A is 0, right? This is nothing but A star according to the definition. So my box negation A is nothing but A star. So the moment I have opens, A and B are opens, it agrees very well with the triangle formula I have for empty algebra. So immediately this will give me that M is a T1 algebra, then M is regular if and only if opens of M is a regular frame. So this regular condition will also give me a regular spaces and also a regular frame. So similarly, we have completely inside relation, exactly like how this happens in frames. If you have seen this in frames, it's very similar to that. It's almost the same definition. For C, D in M, we say C is completely inside D if there is a collection of elements in M which are enumerated by rationals such that C is below A0, A1 is below D, and for P less than Q, I get AP triangle AQ. This is very similar to what we have in frames. So now I say it's a completely regular algebra or a T3.5 algebra if one, it is T1 and it satisfies that every open is join of opens with respect to this relation, which are with respect to this relation. So I just put the definition for frames. We have adopted the same relation for empty algebras. So if I have a frame L, we say B is completely below A. If there is a family of CPs such that P is rational and B is less than or equal to C naught, C1 is below A, and P less than Q implies CP well inside CQ. So instead of well inside, I had the triangle relation because they both are same for opens. And then from there, if L is completely regular, we say every element of a completely regular frame is join of elements in this relation. So it immediately follows that if I have a completely regular empty algebra, opens of that empty algebra is completely regular frame. This is because if I have C and D in opens, and if C is related to D, there exists a collection of sets in empty algebra such that C is below A naught, A1, and for P less than Q, AP is AQ. Okay, but now I want to show that this implies completely inside. If I have opens, I want to show this double triangle, it simply implies completely inside. So using this one, C is already open. So this will be box A naught, and box A1 is below D. C and D are already open, so the box is not going to do anything. And then here I get, this is diamond AP less than or equal to box AQ, just a relation. Then this is diamond box AP less than or equal to diamond AP less than or equal to box AQ. So this implies box AP is in relation with box AQ. So I simply made a family of random elements to a family of open elements. It satisfies all the conditions, but instead of A naught, A1, AP, AQ, I have open elements. Box of A naught, box of A1, box of AP, box of AQ. So I can conclude C is well inside D. So I just changed the using the same collection, I made it into an open collection. So once they both agree upon, both the conditions agree upon opens, I can conclude that if I have a T1 algebra, M is completely regular if and only if opens is a completely regular frame. So next we have normality. Normality is like it's adapted completely from spaces and frames. So if I have a frame L, we say it's normal if A join B is 1, and there are elements U, V in L such that U meet V is 0, and A join V is 1, and B join U is 1. So this is the normality condition for frames. We are going to do exactly the same thing for empty algebras, because what this frame does is, if you have a frame of opens from a topological space X, which is T1, then L is normal if and only if X is a normal space. So it pretty much follows to have the same kind of definition for us, which is empty algebra is T4. If one, it is T1, and all the for any closed element C meet D is 0, there exist open elements U meet UV such that U meet V is 0, C is below U, and D below V. I mean, if you recall what normal in topological spaces, it's simply this, right? You have two closed sets which are empty. Then you can find open sets such that they are disjoint, and the closed set is inside one open set and the closed set is inside. It's exactly the same thing happening with elements now. So now I can conclude that if M is a T1 algebra, M is normal if and only if opens of M is a normal frame. And every normal empty algebra is regular. I wanted to prove this, but then I thought I'd just skip it. So I'm not proving this, but this is a very easy proof to do. It's every normal empty algebra is regular, the regular algebra. And then we have very similar to what we do Urizon's lemma in topological spaces in empty algebra setting. So I just want to quickly do this small lemma because just, you know. So M is a normal empty algebra, and I have a triangle B. Then I want to show that I have an open in between them always. There is an open in between them in the triangular relation. So again, this implies triangle A is below box B, the relation. And this implies box A, diamond A meet negation box B is 0. And now I'm ready to apply my normal condition because this is closed because it's diamond A, and this is closed because box B is open. Negation of an open is closed. So I'm ready to apply my normal condition. So this implies there exists open such that U meet V is 0 and diamond A is below U, negation box B is below V. So this is nothing but negation V is below box B. And then this condition, U meet V condition, will give me U is below negation V. Because U meet V is 0, I have U is below negation V. So I can immediately get diamond A is below diamond U from here. Diamond A is below diamond U, and this is below diamond negation V from here, and this is below box B. Why? Because this is nothing but negation V. Because V is open, the negation V, so negation V is closed. So diamond of a closed is just negation V. So I get this, and then I have A is in relation with U triangle. So using this, we can actually prove that Urizon lemma for the empty algebra version. Suppose you have an empty algebra and you have A is open and C is closed, such that C is below A. Then there exists a family of opens such that C is below U0 and U1 is below A. P is less than Q implies UP triangle UQ. This is very similar to the complete A well inside relation, but the thing here is, if you have a closed element below an open element, that's when this whole thing happens. That's where the Urizon lemma comes in, this closed and open thing. And so now, if I have an empty in the normal algebra, then the completely well inside will coincide with the triangle. I can prove that, but it's fine. So that's also an easy proof. It all follows something like this, just encoding the proofs. So if I have a normal empty algebra, then M is complete algebra because of this. If you remember, completely regular is join of all the opens which satisfies this condition. And the regular is all the opens which satisfy join of opens which satisfies this condition. So previous slides, we saw every normal algebra is regular. So then now regular is also completely regular. So that's why every normal empty algebra M is completely regular. So I wanted to add this. This is again an open problem for me. So I just try to put all my open problems because if anybody has an idea, I would really appreciate. So yesterday we saw that if you have a T0 algebra, atoms of that algebra gives me T0 space, and also same with sober, T1, T half, T2, T3, T3 and a half. Like all of this will actually give me that. If I have an Ti empty algebra, the atoms make a topological space which satisfies the separation axioms. But the problem is with normal. So suppose I have a normal empty algebra, the atoms of my normal empty algebra will not give me a normal space. And for quite long, I was trying to prove it and it was very difficult. Then I think 2023 BLAST, somebody gave a presentation where they were talking about, it was something maybe everybody knows, I didn't cross my mind. The subspace of a normal space is not normal, right? It's not true. It's not true only for normal. Subspace of a Hausdorff space is Hausdorff, subspace of a completely regular is complete. All the subspaces satisfies that. Only normal doesn't. So that's exactly why I realized that the atoms of M may not satisfy this because atoms of M somewhat sit like a subspace in an empty algebra. That's what I call relativization. You know how in topological spaces, we have a topological spaces, we take the subspace topology. We have very similarly, we can do it in the empty algebra by taking the interval of an empty algebra, giving a subspace topology. So that's what I call it relativization. Because in spaces, it fails. Here, the atoms of M are nothing but like a relativization of an empty algebra. I don't have the fact that atoms of M are normal. Maybe true, maybe not true. I don't even have a counter example for that. So if any of you have any input for that, I would appreciate that. Okay, so now this is all I have to say about the separation axioms. Now I will move on to some of the topological properties and maybe talk about the duality in the topological properties. Oh, just a quick recall from what I did. So in an empty algebra, we have T0 separation, but in frames, we don't have anything. Sober, we don't have anything in frames because sober gives you spatial frames. So, and then T half, we don't have anything. But T1 we do have, but only one-sided. Once you have an empty algebra T1, you get the opens to be subfit. And Hausdorff also, we just got one way, Hausdorff frame. But from here, from regular onwards, they agree upon very well. From regular, completely regular, normal, they are equivalent to each other. So next I move on to something called as Scott open and compact. So a filter of a frame is Scott open if join of S is in F implies there exists some finite subset of S such that join of T is in F. Okay. You see, this is somewhat related to compact, right? So you will see it is kind of. And then next, I want to do this in an empty algebra setting. So once I have an empty algebra, once I go to my opens, I want to get my filters to be following this. So what I do first is I first define what is an open filter. Open filter is just when A is in F, box of A should be in F. That's just an open filter. And then Scott open filter, I will just define it like how it's in the above. It's the same thing. I've rewritten it in a different way, but these two are exactly the same thing. An open filter is Scott open if for each directed family of opens, join of S in F follows that S intersection F is non-empty. And I'm going to call the collection of Scott open filters to be S filt of M. And then compact elements, this is very similar to what we have in topological spaces. An element is compact if whenever the element is below join of open elements, it follows that there exists a finite subset such that A is below join of the finite subset. And I'm going to denote K sat of M to be the compact saturated elements of M. So just to quick recall, saturated means meet of opens. That's what saturated for me, meet of open elements. So what is the compact empty algebra? It has just the top has to be compact. When I say top, it's just one has to be compact. It's very similar what happens in frame. A frame is compact if one is compact. So it's the same here. And then now very easily, I get an isomorphism between Scott-open filters of an empty algebra and Scott-open filters of opens of an empty algebra by this just intersecting the Scott-open filter with opens of it. Actually, just F2, F intersection O of M is a isomorphism between open filters and filters. If you have an open filter in empty algebra, you get a filter here. It's vice versa. Then you restrict it to Scott-open filters. We get a isomorphism between Scott-open filters. And I want to show using the compact property that finite intersection property for compact empty algebra. I'm pretty sure everybody would have seen this in topological spaces. So I just wanted to show how it's as easy as you do it in topological spaces to do it in empty algebra setting too. I'm sorry if the proofs are, yesterday I got wild and I thought, what are the proofs I'm missing from my paper? I just included so that I can do it today. But if it's boring, I really apologize. So let me prove. Suppose A is compact. Suppose A is compact. And then F is a collection of closed elements with A meet of F is 0. Okay. And then this is always I do. A is below negation of meet of F. All right. And then the negation of meet is just join of negation of elements of F. I just took the negation. But A is compact. And these are open because F was closed element. So negation of F is just open. So now I can find a finite of them, right? Because A is compact, I can find finite of them. And then I put it back. This is A meet Fi. That's the first one. So whenever you have A meet of F is 0, you can always find a finite subset which does that. So suppose conversely, on the other hand, I want to show A is compact, assuming the condition holds. Suppose A is below join of some open elements. Then I have same thing, meet of negation of join of S is 0. This is A meet of negation S. Because S is open, negation S is closed. And I can apply the condition. I get finite of them. And then A is below join of Si. So A is compact. So finite intersection property is pretty much true in the empty algebra setting too, because it's easy. To be honest, the moment I have started to think everything in algebra setting, and it's quite easy for me, but maybe not for topology people, but it's easy for me. And very similarly, you can see that M is compact. Instead of doing the same technique, instead of A, I just replace it with 1. Because when I say M is compact, I simply mean 1 is compact. So, and then we can easily get the other one too. It follows quickly. So now I want to talk about the Hoffman-Mislov theorem. I don't know if you have heard this theorem before. This is a very well-known theorem. It's a duality between compact saturated sets and the Scott open filters. Okay, so I'm going to derive that using empty algebra. Why? I don't think so. I'm the first one to do this. I think there is a paper with Guram and Sebastian. They did it. They did Hoffman-Miss law without using Zorn's lemma. It's just, it uses prime ideal theorem. I think mine also just uses prime ideal theorem. It doesn't use Zorn's lemma. But I think there are so many people who have done that before, so I'm not sure. But yeah, I just use prime ideal theorem and Zorn's lemma, which I don't care, but people care, so it's okay. So this is the theorem I use for proving Hoffman-Miss law theorem. Keimal-Paseka lemma. This is a I think everybody should give it a read. It's amazing. It's a very nice proof. It's just a small paper. It just has 3 theorems in a paper. It's very nice. So I think it's a good one. And I have proved the same theorem in empty algebra setting, but I don't use Zorn's lemma. I just use prime ideal theorem. So if M is a sober empty algebra, F is a Scott open filter, and then meet of F is below U, then U is in F. The only condition is U has to be open. So if you actually see that paper, you will see it's exactly the same thing. Instead, you will have intersection of U belongs to intersection of F, and then U belongs to F. That's exactly how you will see. It's a very nice proof. Okay. And if you get a chance, you should give it a read, my paper too, because it doesn't use Zorn's lemma. Just use prime ideal theorem. Okay. Now, Hoffman-Miss law for empty algebra. So if you remember, I told K-SAT stands for compact saturated elements, and S-FILT stands for Scott open filters. So if you have an sober empty algebra, this is isomorphic. The poset of compact saturated elements is isomorphic to Scott open filters. And to prove this isomorphism, I use the map alpha of S is A in M such that S is below box A. This is a and then now, how well does Hoffman-Miss law I have sit well with the Hoffman-Miss law for spaces, Hoffman-Miss law for frames? Suppose I have a frame and Scott open filters of a frame ordered by inclusion. I first showed that the posets of a Scott open filters of a frame is isomorphic to Scott open filters of opens of points of L. The opens of points of L. These two are isomorphic. And then using that, I just show that if I have a frame, and then this is the points of a frame, then Scott open filters are isomorphic to compact saturated elements of points of L. So this is something to observe, that here, if you see, you have to get this isomorphism, you have to go from a Scott open filters of L. On the other side, you need to go to the space, compact saturated elements of a space. But in an empty algebra, what I have here is both are in M. I don't have to leave my empty algebra. Compact saturated of empty algebra, isomorphic to Scott open filters of empty algebra. I don't have to leave anywhere. They both leave inside my algebra. Yeah, and similarly for topological spaces. If I have a topological space, compact saturated elements of a space is just compact saturated of the empty algebra, power set algebra. Then I can immediately get that Scott open filters of opens of X is isomorphic to compact saturated of X. Again, here I want you to notice here, this is in space, right? Compact saturated of space. And then you have to go to the opens to get the Scott open filters. So again, in empty algebra, you can catch everything in one algebra. You don't have to go to the different functor. Here you had to go to the spaces, here you have to go to the frames, but in the empty algebra setting, we have everything in the empty algebra. Yeah, now I am ready to start with the dualities, and this Hoffman-Mislov theorem will be used in the proofs to prove all these dualities, but I'm not going to prove the proof, so it's okay. So we have Hoffman-Lawson, Isbell, and Stone dualities. I think I'm going to include more of it, but we will see as I discuss. So topological space is locally compact. If for each open set U and X is in U, there is an open set V and a compact set such that X is in V, inside K, inside U. I think this is a definition of a local. There are so many other definitions of a locally compact, and once it is Hausdorff, everything becomes the same, but it need not be Hausdorff. So I am going to consider this definition. I'm going to exactly translate this to my empty algebra version. Oh, and this is maps on the compact saturated one. If I say a continuous map is proper, if F inverse of K is compact for every compact saturated K. See, F inverse of K is compact is enough because F inverse of saturated is always saturated anyway. So it's just F inverse of compact is enough. And then this is the relation I'm going to define. A, I have not given a name. So A, I don't know, this looks like a mouse to me. Okay, A less dot B, if there is a compact element such that it sits in between A and B. If you compare to the topological spaces, and here you can see you have an open set V, you have an open set U, and you have a compact element in between them. It's the same thing. You have an open here, you have an open here, you will have a compact. But right now I'm not defining for opens, but once I go to locally compact, I will. And then now here I define for opens. So suppose M is locally compact, every open is join of open such that V is in relation with that. That exactly gives me this. So I literally translated the topological space to the empty algebra setting. But again, we do everything in a generation way, so I have that. And then morphisms the same way, because here it's an inverse. For me, it's just a morphism. So I say an empty morphism is proper if compact saturated goes to compact saturated. I could have restricted to compact saturated goes to compact because this is an empty morphism. It's a complete Boolean homomorphism. So saturated goes to saturated. And then I have a way below relation and continuous frames. So in order to compare locally compact, on the frame side, we have continuous frames. So I'm going to define what continuous frames are. So way below relation is A, way below relation B, provided whenever B is below join of S, there exists a finite subset T such that A is below join of T. I know we have seen so many relations like this today. So this is way below relation. And I say a frame is continuous if every element is generated by elements with this relation, which agrees upon this relation. And then a frame homomorphism is proper if it preserves the way below relation. So here, if A and B are in opens, then these both relation agree upon each other. That if M is locally compact, then A relation B if and only if A is way below B. I don't know if I have time to prove this. Maybe no. So this relation agrees upon if it is locally compact. And what happens next is exactly what happens in topological spaces and frames. Like if you have a sober space, opens of a sober space is continuous if and only if the space is locally compact. So I'm going to get exactly the same thing what we have in topological spaces. If M is sober, opens of a sober empty algebra is continuous if and only if M is locally compact. The only thing which is not true in my case is, not in my case, our case is, if you have a continuous frame, it's always spatial. Unfortunately, we don't have that. We don't get that. We don't get this to be spatial. So now Hoffman-Lawson duality, I'm just going to define the categories. LC sob will be locally compact sober empty algebras and locally compact sober spatial empty algebras, and continuous frames, locally compact sober empty algebra, sober spaces. And now I get an adjunction between locally compact sober to continuous frame and locally compact sober to continuous frame, and then an equivalence between spatial parts. I really want to write this because I think I'll be. So locally sob empty to continuous frame. And then once I make it spatial, I mean, I have so. And then this becomes an equivalence once this is spatial. So in spaces, once you have locally compact sober, there is an equivalence between continuous frames and that, but I don't have that. I have to add spatial to make it an equivalence. I need this. In my empty algebra case, we need this. We need spatial to make it dual equivalence. Oh, I went far ahead. Yeah. So then using that, I get this is Hoffman loss on duality. Continuous frame is dually equivalent to locally compact sober. So I get the dual equivalence from this. So this is what I don't have. Again, this is also an open problem. I want to see if locally compact sober gives me a spatial, I mean, continuous implies spatial. We don't have that. That's an open problem too. And then we restrict locally compact to stably locally compact. Now, stably locally compact is usually, I think Sebastian discussed this a little bit. I'm not sure, I don't remember. So compact, intersection of compact sets are not always compact. So if you have two compact elements, the meet of the compact, if they're compact, then it's going to be called as stably locally compact. And then we say something is stably continuous on the frame side if L is continuous and the way below relation is stable. That simply means you have A way below B, C, and A way below C implies A way below B meet C. Just like the meet and the meet here, they have to follow. So now on the empty algebra side, I have stably locally compact, and on the frame side, I have stably continuous frames. So again, now if M is sober, opens of M is stably continuous frame if and only if M is stably locally compact. So whatever we did for locally compact, now it is for stably locally compact and stably continuous. So again, the same thing, I'm just gonna run through because it's the same thing. You have LC SOP to stably now and spatial, and then continuous to stably continuous, and then locally compact sober spaces to stably locally compact sober spaces. And then the adjunction we had here will now restrict to stably locally compact, and the equivalence will restrict to stably locally spatial empty algebras. And then this is my last slide, I guess, yeah. This will be same thing, now stably locally compact. I went to stably compact, I just want to write it. Now after stably SOB, I went to, after locally compact, I went to stably locally compact. And now finally, I'm going to stably compact, which also includes SOB in it. So now from locally compact to when I restrict it to compact, I get the dual equivalence. Again, the adjunction restricts and the equivalence restricts. And oh, no. Yeah, I want to stop here for today.
Thank you so much, Ranjita. Some questions? Some questions, comments?
Can you share again the definition of continuous frames?
Yeah. Oh, no, I'm going forward.
And where does this definition come from? Is yours or from another source?
From zeros?
No, where this definition comes
Oh,
from?
this I took it from Frames and Locals book.
Putre and
yeah,
Picado. Yeah.
Frames
Okay,
and Locals
thanks.
book, yeah. Yeah, my frames, all my definitions are from that book.
Okay.
All my definitions.
Thanks.
Another question? No? Well, thank you so much, Renita.
Well, our last speaker this morning is Santiago Martelo Gómez from Universidad de Investigación y Desarrollo UDI, Bucaramanga, Colombia. So thank you so much, Eder, for coming. The title of his talk is Periodicals as Keys to Understanding Structure in Pure Semi-Simple Hereditary Rings.
Well, first of all, I want to say thank you for the organizing committee for the invitation. And thank you for everyone that came today for the talk. My presentation today, it's called Radicals as Key to Understanding Structure in Pure Semi-Simple Hereditary Rings. It's gonna be like an introduction first. I want to talk like a little bit of background, what motivated our research in these rings. And I'm gonna end with future research opportunities. Well, the study of pure semi-simple rings has been like a new topic that has captured the attention of many algebraists to their complex structure and significant implication of model theory and representation theory. On this talk today, I want to show how periodicals can provide essential insights to understanding the structure of these rings. I'm going to present recent and relevant findings that address the connection between periodicals and the decomposition of models in pure semi-simple hereditary rings. It's well known that in module and ring theory, there are many ways to define a ring. So it's very important to classify them. So if we read about the literature around this classification, most of this classification has been through category of models. However, lately here in Mexico, like for the past 20 years, it has been like very interesting to do this classification using the lattice of radicals. Well, as we saw yesterday in the talk of Hugo's talk, he defined a radical as un factor of the identity functor. So we have this definition here that is what a radical is about. A radical over a ring R is an assignment that fulfills these two conditions that can be resumed in what I just said before. Also, we have this definition of special radical, which is idempotent radicals, that we can say this only means that applying sigma twice has the same effect as applying once. Here, this is not a definition, but it's an implication of definition of a radical is. However, I found this one like more attractive to present today. And we call a radical if and only if sigma of m quotient sigma of m is equal to zero. And I want to say that there are many examples of radicals like we saw yesterday in the last talk. However, we want to describe lattices of radicals in pure semi-simple rings. And before I start with them, I want to open a specific case, which is a very well-known example, these semi-simple rings. We all know the structure that is known about the Wedderburn-Artin theorem that says every semi-simple ring can be expressed as a finite direct product of matrix rings over division rings. And the characterization through the module category says that every module here is projective, is injective, and we have a decomposition that every module can be expressed as a direct sum of simple modules. And the most recent characterization we have about this ring is through the lattice of radicals, through the works of Reyes Rios Rincón, Fernández Alonso, and Signoret. But basically, we found the characterization that says that this lattice is a finite Boolean lattice. So we have this example here. If we take an Artinian ring, we can have the lattice like this one. Remember, like to talk about lattice, we need an order that we saw yesterday, that we say upper radical, it's less equals than sigma is less or equal to tau if and only if sigma of m is less equal than tau of m for all m in R mode. So with this order, we get a lattice. And for semisimple rings, we found these lattices. As example, if we have two simple rings in a semisimple ring with ST, no isomorphisms models, we have these lattices, and we have this one for three simples. So we wanted to like try to see if we can extend this result that we had in semisimple rings in a broader class, which is the pure semisimple ring. The motivation is basically because the pure semisimple conjecture has been a central topic of interest in ring and module theory. Around the 60s, Robert Warfield was the first one to talk about this conjecture. There are many ways to define a pure semisimple ring. We have left and we have right pure semisimple ring. So this conjecture says that a left pure semisimple ring, it's also right pure semisimple ring. And this implies that every pure semisimple ring is of finite representation type. This means that there is a finite number of non-isomorphism in the incomposable models. And we have, on the research about the little background, we have too many authors and mathematicians that work around solving this conjecture. We have, for example, Daniel Simpson, that have worked towards proving or disproving this conjecture on many papers. And most of the results are like related to try to solve this conjecture. So as I said before, I want to extend what we had in semisimple rings, but now in pure semisimple rings. So this is the first definition. A ring R is left pure semisimple ring when every R module can be expressed as a direction of left in the incomposable submodels. And I put this left, but the analogous can be defined for the right. So if we have a module M, and we have submodules, all of them in the incomposable, and if we can express this module as a direct sum of an incomposable module, then and it happens for every R module M, then we say we have a pure semisimple, a left pure semisimple ring. So in the characterization about the category of modules, we have this. R is left pure semisimple ring if and only if every pure such sequence of left R modules splits. We have every left R module is pre-injective. These are like definitions equivalent, similar to what the definitions are in semisimple modules. However, it's a little bit different, right? But I'm going to focus in the four characterizations that we have here, that we can express every R module as a direction of indecomposable models. Preradicals can be considered, as I said, as a functor of the identity functor that are submodule within a category. But one important property that provides what we saw on the lattices of semi-simple ring is that the radicals preserve this property here. Sigma applied to a direct sum is the direct sum of sigma applied to each one of in the incomposable module in this case. But this happens for every direct sum, but particularly in our case, it's gonna be around in the incomposable modules. So the big problem we have compared with semi-simple ring is like when we express a module as a direct sum of simple rings, a radical only has two different ways to be calculated. It can be the any trivial module, like it's zero or it's the full module. However, the lattice of submodule of an incomposable module can be very thick and very different from the first one. And also it has been like something studied a lot, how to describe lattices of submodules of the incomposable modules. So using this property, we can say that preradicals, the study of preradicals can be directly studied by their values on the incomposable modules. So for do this research or try to describe lattices here, we use a tool that it's the partitions of Rint. Now, as every module can be expressed as a direct sum of incomposable modules, and we don't have too many information about the lattice of submodules, then we use this alternative option, which is using a partition of the set of Rint, which is the full set with all the non-isomorphic in the incomposable modules. So, but what is this partition? An X-injective partition of Rint is defined as this one. The first condition is only for being a partition, but every set of this U alpha is not empty and finite. And for each alpha less than lambda, U alpha contains all X-injective modules with it. The union of beta less equal than alpha, the U beta. And just to make it clear, if we have C a subclass of R mode, we say that X in C, X injective module in C if X to 1 R, Cx is equal to 0 for all C and C. These partitions were well studied by Dung and Garcia into many works of their research, and they found too many interesting properties about this partition that I'm going to use a few ones of these properties to try to describe the lattice of radicals in pure semi-simple rings. Also, we have another partition that was studied just like before of this past one. This one was studied a lot by Huizgen and Zimmerman, and is a strong projective partition. So instead of the third condition is every set is, how can I say it? Every module that belongs to every section of this partition are X-injective modules, but here now we have, this is formed by minimal cogenerated set of this same part of the partition. But now this partition looks very nice, but we don't know when can we use it because What guarantees that the partition exists? Well, Huygens Zimmerman proved in many of his articles, one of his article, that if R is a pure semi-simple ring, then Rin has a strong projecting partition. Even more, he proved that the pure global dimension has to be 0 for this partition to exist. Dung and Garcia proved that if we are not only in pure semi-simple ring, but we add the condition to be hereditary ring, then we're gonna have that this partition, we can have this partition on pure left hereditary rings. Here, I'm gonna try to explain how this partition works and what properties this partition has. So if we take the X injective partition and we take like this set U alpha on this partition, and we take a model X on this partition, but also we take another set U kappa with kappa greater than alpha, then we could find morphisms from Y to X. However, but we do it in the other side, taking like a model Z in U beta, we don't find any morphisms. There are no morphisms from Z to X or to Y. This means like we don't have morphisms from the left to the right in this partition, but we can find morphisms from the right to the left. So it's a really nice behavior of this partition about morphisms. It's very well organized. But also, another properties in general that this partition has is that, for example, in the first block of this partition, we can find all the injective indecomposable models. All the injectives are here in U0. However, the projective ones, we only in general ones, I mean, without adding this condition of the ring to be indecomposable, we can find like the last block of the partition, all models that belongs to this block are projective, but it doesn't mean all the projectives are in this block. We can find projectives everywhere here. But if we add the condition of the ring to be indecomposable, then we can find it in these like final consecutive blocks in the end. So there are too many properties about this partition, but then when we go for an special case, which is a pure semi-simple hereditary ring, R, with exactly two simple models, then, first of all, since it's pure semi-simple hereditary ring, this ring is gonna like have an X-injective partition. And it's also proof in the article of splitting torsion pairs of Tungar Garcia that these sets here, the number of indecomposable models is going to depend on the simple models that the ring has. For example, for a ring that has two simple models, every set up here is going to have a maximum of 2 models, which is the simple ones. We're going to have 3, the maximum is going to be 3. The special case is going to be always the last block of the partition that we can have like a block that is less than the number of the simples. So using this condition of the ring of being left pure semi-simple hereditary ring, we're going to have a partition, X-injective partition, that is going to be formed like, for every set is going to have two indecomposable models. Then with this same partition, we express it as this linear order with some other property that this partition has. And this linear order here is gonna like get even more properties. For example, one of the properties that this partition has, this linear order, pairs is like this one here is gonna be the simple one model, which is gonna be the injective. This one is the other simple, which is gonna be the projective. This one is projective, but not simple. This one is injective, but not simple. And we have many models here. But as the same property as the X-injective partition, we don't have morphisms from the left to the right for every model here in this linear order. But we can find morphisms from the right to the left. Also, it's been proved by Dung and Garcia that if we take two consecutive models and we do the direction of them, then we're gonna have tilting models. What other properties here? Another special properties that are implied by the works of Dung and Garcia is that here, if we take, for example, alpha less than beta, and we use M alpha, and M beta, then we have two nice properties here. For example, we can say the model M alpha finitely cogenerate the model M beta. And this happened in the order of this new linear order we have here. But also, we can say this. The model M beta finitely generates the model M alpha. And it happens for any model that I can take with this ordinal, alpha less than beta. So these properties here can be translated in some properties that we're gonna use to describe radicals. But before that, to use these nice properties on this partition, I want to define a new category which was a really handful tool to describe also the radicals. And it's this one. In the context of model theory and triangular matrix rings, we can define new objects formed by this triple BWG, where this B is a left X vector space, W is a left G vector space, and we have this G linear map. Here, F and G are considered to be division rings. We can, in this new object that we define in this new category, we can define a morphism between the objects here to be a pair of morphisms, well, linear maps between these F linear spaces of G linear spaces that makes this diagram to be commutative. So this commutative of the diagram ensures that the pairs AB respect the structure of the model in the category of triples. So how the process works with this new category and how it can be related to the pure semisimple rings, and how can I use it to describe lattices of radicals here? Well, let's gonna assume that we start with a left pure semisimple hereditary rings with exactly two simple models. Then we get from the past results that we can order R in with that linear order that we talked before. Then any ring that is left pure semisimple hereditary ring can be expressed as this triangular matrix. And it has to be with properties that these rings fulfill. For example, the ring R first, what we consider basic to split this ring as the direct sum of two projective modules, where this one here is the simple one, simple projective. And this one is the non-simple projective. Using this representation of the ring R in this kind of rings, then forming the matrix, this one, it can be proved that S is isomorphic to the ring R. And also by the result of Dungan and Garcia, in these rings, especially when we take the how do you call it? Endomorphism set, in the endomorphism ring of the indecomposable models, every one of these in endomorphism, it's a local ring. It's a local ring, and also this one here is a bimodal over these two ones. Something else about here. So with this result with Dungan Garcia, when we are on the pure semi-simple hereditary ring with two simple models, we can represent these rings as this one, keeping in mind that F, this one, G, this one, and B is this bimodal here. And now, with the last category that I just defined, we can see that the category defined before and the matrix, the triangular matrix ring of this form are equivalent categories. And there is a way to see this equivalence. For example, if we take an object of BWG that normally you just name it like this. When we talk about objects, normally we have to present like this object, but we reduce this representation by just taking objects like this. And to go to the category of these rings, we only take the object here is gonna be B plus W. And we can define the operation of over here, like, for example, if we take A, 0, B, C for BW, we use this one, like we are multiplicating matrix, but in this last one, we use this representation here with the linear map. And we get one side. The other side, if we take ring like this, we take like model here in the matrix ring, then we split M as E product M plus 1 here, where this one can be taken here. And this one is gonna work like F vector space, and this one can be taken as the G vector space here that we need to complete this representation. So what properties, implications, and radicals we get from the linear order that I just described here? The first one and the first result we got on the research is that if we have a radical sigma and any ordinal alpha, then we got these four properties. It says like, for example, if we don't take in consideration the first model, which is the simple injective, and it happens that for any alpha, the radical annulated, then it's gonna annulate every model after it in the linear order. And we can see it through this property, this one, because if it annulates something that is after it, sorry, before, radicals fulfill this property about direct sums, we can split here, and since it's gonna be 0 in sigma alpha, then we're gonna get sigma of m beta is gonna be 0 too. Second one says like, if we don't take the last model, and it happens that it let fixed the model m alpha, and it's gonna like let invariant, it's gonna say, well, not invariant, fixed for all of this. So how this works, going back here, these two properties can be seen like this. For example, if we take up a radical sigma, and for any reason this radical annulates this one, then it's gonna annulate all the modules after this module. So sigma m kappa is gonna be m kappa is gonna be 0 from there. And if for any reasons in this linear order it doesn't happen that it's equal to 0, but for example here we have m beta, well, is this one. It's gonna happen like the same but in the other direction. It's not gonna be 0, but it's gonna be let fixed all the model after, before it. Is how can we resume these two properties, first and two? But it only happens if we take in consideration, for example, this one only annulates if it's not the first one. And the second one says it let fixed is not the last one. But what happens if, for example, it let fixed the last one? It's not gonna imply that it's gonna fix all before it, but we can have this nice property, like the circle of the model, which is the direct sum of all the simple models included in M alpha is as a model of sigma of M alpha. And if the radical for some reason annulates the first one, then the radical applied to the any model is going to be as a model of the circle of M alpha. We can see like if we combine 3 and 4, I mean, in this linear order, we have a radical which let fix the last one and annulates the first one. Combining two of them, then sigma applied to M alpha is going to be the circle. This is another nice property that we got from these properties from the partition of Rn and the linear order. Is like if we take any radical, sigma, different from 0. Well, we can include 0 here because sigma squared for when sigma is 0 is also 0, but if we take any radical and we have that it annulates the first one of the linear order and the last one of the linear order, the radical fulfill this property, which square is equal to 0. And there is analogous way when it let fixed the first and the last module of this linear order. When it let it fixed, then sigma squared is not 0, but now is equal to 1. Then, to try to go and describe the radicals here, we thought about a nice way to represent any radical using this linear order by this. We say like a radical is equivalent to this representation if each one of these models here are the values of this radical in each indecomposable model of this linear order. So this is a helpful way to represent them and work with them, because what we want to try is to see how radicals behave on these rings. So using this representation of the radicals, then we characterize first the idempotent radicals. Remember, the idempotent radical is when we apply it twice, is the same effect as the first one, right? So if we have an idempotent radical sigma, then we can describe how sigma is going to look like on these rings. First, well, we have the radical 0. We have this one that here we can see how it works, the previous result combined 3 and 4, which is say like when the first one is annihilated by sigma and the last one is fixed by sigma, then all of these models are the sublaw of each of the indecomposable models here. And this is a special radical. It's also is not only idempotent, but we're gonna see it's also a radical. We define this iota beta like this, and we can see iota beta how it works. Iota beta, it's like in the linear order when after we represent the models. This one is like, if we take the linear order until m beta, we have here like, it's gonna be fixed. We're gonna let the first one in the first one, the second one in the second one, until here, when it's gonna start with the sublaw. So instead of here, this sigma is gonna be applied to sublaw, and we're gonna have just sublaw. The last one, which is sigma m lambda plus 1, since this is projective and simple, its sublaw is just itself. So we're gonna have this one, m lambda plus 1. Also, here we can find these special radicals here that are also radicals. And these one are related to torsion theories, because since we have here in the linear order, this is all the set are int. Dunga Garcia defined in one of his papers that every time we get a partition of R int, of this one, and we got this to happen, like for every DND and from every CNC, they call it a splitting torsion pair. Any splitting torsion pair here are associated to torsion theories in all the category of model here. And these radicals that we call gamma, if we take, for example, a partition here, we call it this linear order by the first one, we're gonna have a split interaction pair. We're gonna have, for example, D is gonna be this one, C is gonna be this one here. And we call this one gamma 0. We basically do is let fix it the first one, and the rest is just 0. Here we got gamma 1, let fixes this one, the rest is just 0. This one, we have this gamma alpha, and instead here we have like an order. Or gammas, which we're gonna see these ones are also radicals. And the last one, it's the radical identity. An indication here to prove this theorem, especially, well, the second one, it's the combination between 3 and 4 of the previous result that I present. However, the third one here has to be with, for example, if we take, this is just a hint, how can we prove this theorem? And it works like as an example, how to prove the 2 other theorems that I'm going to present. If for some reason, for example, I'm gonna start, let's gonna assume that this proradical, let's fix it here, 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 until this one. And we don't know what's here, right? So since this is a submodule of the indecomposable module M alpha, if it's 0, then it's going to annulate the rest of the tail of this linear order, which is going to imply it's going to have the fourth one, which is the proradicals gammas. This one is going to be gamma alpha. So if we assume it doesn't annulate here, we can assume it happens to different options. First, it's going to let it fix it to M alpha again. Or if not, then we can say M alpha is less than, it's a submodule of M alpha 2, proper submodule. Then, since we are on left pure semi-simple ring, we can express this new module, which is a submodule of M alpha, as a direct sum of indecomposable modules. However, since this is like, in this decomposition here, we're gonna have that we have indecomposable modules where alpha is gonna be greater than, kappa is gonna be greater than alpha, less equal lambda plus 1. And why? Because if we get in this decomposition, a module, indecomposable module with an ordinal less than alpha, then we're gonna have amorphisms from the right to the left. So from the left to the right. And then it's gonna have, it cannot happen because of the properties of this linear order. Then doing this decomposition, we say that it can happen. There exists this one such that M kappa appears in this decomposition. In case it happens, like if we have, for example, that in the decomposition of this module here appears something here, Then since this radical is idempotent, we can apply it again. So if we apply it again, we're gonna have sigma squared, and alpha is gonna be just sigma. And since radicals fulfill this property about direct sums, then we're gonna have two different decompositions. For example, we're gonna have here something like this. We're gonna have this one. Well, here we can put an indicator here that is like, it has to be just a single one. It can be like many copies of this kappa here. So we're gonna have this one to be equal to this other decomposition. Then again, we can split this one here because we are in a pure semi-simple ring. We can split every single one of them as direct sum of the decomposable models. And then we're gonna have two representations of one model as different in the decomposable decomposition by using a theorem that is called Kurzschmidt-Asumaya theorem that says that this composition has to be a unique, how do you say that? Unique salvage isomorphisms? Well, up to isomorphisms, yes. So then we will have to get, in the end, that there has to be one of these decomposition. They're gonna exist a kappa that this radical let it fix it. And using this property, if let it fix it, for example, here, it's gonna let fix it to the left, all of them. It cannot happen. It's gonna like be a contradiction with this one because we are assuming this condition here. So this is like the hint how to prove this one using the property of being idempotent and the properties of the linear order. And we get an analogous theorem when we describe radicals in the same way. We get, of course, the radicals identity, the 0, 1, this special one that is also a radical too, and this other two. Also, the proof of these both theorems depends on these two, the first and the last one. Because here we can, since these two are simples, when we apply a radical here, we're gonna have, for example, here is only m-1 or m0. Here we're gonna have sigma applied here is gonna be just this one. And combining the four possibilities using the simple models, we can divide. Every time we take a consideration here, for example, not fixing the first one, annulates the last one, we're gonna get conditions that imply any of these results here for the idempotent, also for the radicals. And then we try to see, based on these two theorems, try to extend it because only here we have idempotent, we have radicals, but we don't have so much more here. So then we got like this new theorem that try to extend how can we describe radicals in the pure semi-simple hereditary rings with two simple models. And there are implications here. For example, the types of radical that exist in the pure semi-simple rings, how can we see it? How a radical is uniquely determined by its values across the definitively generated in the composable R models. And we get an example here. This ring here, which is when we take K, a field, and lambda to be the pad algebra generated by the quiver A2, this can be represented as this matrix ring, which is, as I said, this is a pure semi-simple ring with two simples. So the decomposable models here, we got three that we can see it when we talk about this path algebra, we use the Slaughter Clayton diagram, which is this one, that this diagram represents all the decomposable models and all the morphisms that we can find here. This one, we can see the order, the linear order that we describe from Duran Garcia. The first two ones, which is these two, I'm gonna form the first block of the partition in the X-injective, which is formed by the injective ones and this one projective, and we split it, we're gonna get like a linear order formed by three decomposable models. And using our characterization of radicals theorems, we get all the radicals here. We get 8. But in the first one, we got 2. For example, we have the 0 and the first one, which is the identity. And we have this, the rest, just applying the theorem that I present about how to characterize them. And then we can see now how can we see or diagram of the lattice on a pure semi-simple ring looks like. We also have the lattice of the idempotent. The radicals is just the same, but doing like the opposite one. Here in this row, we're gonna have the gammas. And here we're gonna have another radical that is called rho, that is in the theorem, but it's analogous to this one. Now we can get the lattice of the idempotent radicals to look this way. So by finishing like this talk today, I want to say that we got this example, we got this theorem, but we want to do is to extend this result not only for a ring, which is pure semi-simple hereditary ring with 2 simple models, but we want to extend it even if we get, for example, 3 simple models or a general case with n simple models. And also try to see if we cannot use the hereditary condition just to be pure semi-simple ring and see how it works. It's a long path, but I would say we started with an objective. Now in our research, we are currently working to establish a Galois connection to better understand the structure of the radicals. And we can establish this one by using a joint functors associated with triangular matrix rings to define connections within the lattice. And what do you expect? Well, get insight into how the radicals interact in rings with finite representation types and deepening structure analysis. What we want to do is characterize finite representation type first, because it's like simple. It's easier, let's say. It's not easier, but it's less complicated than the general case. Develop application, practical application, extend this application, structure analysis in fields that are non-modular and ring structures that we can apply to representation theory and category theory. And provide tools to systematically analyze relationships within model lattices. Well, we have many complex problems here. I'm gonna say this one is the first complexity that we find. It's the Galois connection. We're doing like a great work until now. I want to extend what we already got that I couldn't like talk today for time. This is future and conclusion. We want to do is all of these 3, but provide a structured approach to model lattices analysis in pipe representation theory and other areas of mathematics. And that's gonna be like my whole presentation for today.
Comments, questions for Santiago? Oh. Well, thank you so much, Santiago.
Gracias.
¿Alguien desea hacerle alguna pregunta, comentario, opinión? Okay, bueno. Thank you so much. This is our last talk this morning. We'll be back in 90 minutes. Regresamos en 90 minutos, 1 hora y media para comer y coffee break. Aquí abajo hay comida.